We've learned how to determine an empirical formula from either combustion analysis data or masses or percent composition. The empirical formula gives us the lowest ratio of atoms of each element, but the molecular formula is usually what we want to find. And the molecular formula gives us the actual number of atoms of each element in a molecule. So the molecular formula is always going to be some multiple of the empirical formula. We learned how to determine the empirical formula from the molecular formula just by finding the lowest ratio. And so finding the molecular formula from the empirical is kind of like going the other way. You can have several different compounds that have the same empirical formula. In order to find the molecular formula, you have to have the molar mass. Okay? The molar mass you don't get by combustion analysis. There are different ways to get the molar mass. One of them is to use a mass spectrometer, and we're not going to go into how that works. But for your purposes, you have to be told what the molar mass is. Otherwise, you can't do the empirical formula. So, given the molar mass and the empirical formula, then you take the molar mass that you're given and you divide it by the mass of the empirical formula. So you've got the empirical formula, find the mass of the empirical formula, and then see how many times it goes into the molar mass. So you're dividing and you're going to get a whole number. Sometimes that number is 1. And that tells you that the molar mass and the empirical mass are the same. That can definitely happen. If it's not 1, it'll be 2, 3, 4, something like that. Then you multiply the subscripts in the empirical formula by n to get the molecular formula. Okay? So we'll do an example. Aspirin has a molar mass of 180 grams per mole. If the empirical formula is C9H8O4, what is the molecular formula of aspirin? The molecular formula is some multiple of this. All the subscripts multiplied by the same number. It might be 1, it might be 2, it might be 3, we don't know what it is. So what we're going to do is we're going to take this empirical formula and find out the mass of that. So we've got 9 carbons, and each mole of carbon is 12.01 grams. And then we have 8 hydrogens. Each mole of hydrogen is 1.008 grams. And then we've got 4 oxygens, and each mole of oxygen is 16 grams. So, turn on calculator. 9 times 12.01 plus 8 times 1.008 plus 4 times 16. Well, that's no fun. Did I seriously have this as an example? So the mass of the empirical formula is 180.154. Well, if I take the molar mass of the compound, you really don't have to do this, do you? If I take the molar mass of the compound and divide by the mass of the empirical formula, what do I get? Essentially 1. So what's the molecular formula? It's the same, because when you multiply everything by 1, you get the same numbers. So the molecular formula for this compound is the same as the empirical formula. And next time I need to use a different example. Okay, let's do one that's a little more interesting. combustion analysis of a 5.50 gram sample of benzene produces 18.59 grams carbon dioxide and 3.81 grams water. Determine the empirical formula and the molecular formula of benzene, given that its molar mass is approximately 78 grams per mole. This is the molar mass of the actual compound, the molecular formula. Here we have combustion analysis data. We've got mass of carbon dioxide, we've got mass of water, we've got a starting mass of product of our sample, and so we can use that to calculate the empirical formula. So the first thing we have to do is find the mass of carbon and hydrogen and oxygen that was in the sample. So we've got 18.59 grams of carbon dioxide. Well, carbon dioxide is carbon plus 2 times the mass of oxygen, 44.01, right? That's grams of CO2 equal to 1 mole. Well, if I take this mass of CO2, in 1 mole of the CO2, this is the mass of carbon, right? There's the mass of carbon and the mass of oxygen, and they add up together to make the mass of the whole compound. So there are 12.01 grams of carbon in 44.01 grams of carbon dioxide. 12.01 grams of carbon in 44.01 grams of CO2. And that allows me to calculate the mass of carbon, because that CO2 came from combusting the benzene. All the carbon in the CO2 came from the benzene. The oxygen could have come from the benzene, or it could have come from the oxygen that we put in there so that it could burn. We don't know. So I've got 5.07307 grams of carbon. And then I'm going to use the mass of water to calculate the amount of hydrogen, because the hydrogen in the water came from the benzene. There's no other place for it to have come from. It came from the benzene. The oxygen, again, could have come from benzene, or more likely it was just the oxygen that was blowing through there so that the thing could burn. 3.81 grams of water. Well, water is 2 times the mass of hydrogen plus the mass of oxygen, 18.016. And so from our little calculation of the molar mass, we can come up with a conversion factor like this. This is the mass of the hydrogen, and that's the mass of the water. So there's the mass of hydrogen in 18.016 grams of water. .81 times 2 times 1.008 divided by 18.016. This gives me 0.42634 grams of hydrogen. Well, here's our carbon and hydrogen. What do those add up to? 5.07307 plus 0.42634. So these guys together are 5.49941 grams of that original sample. We started out with 5.50 grams. So the difference would be the amount of oxygen. So 5.50 minus that, 5.50 minus this gives me 0.00059. And checking significant figures, that's where the uncertain digit is. Is there any oxygen in this compound? Very little. Okay. So when we're doing this, we do come up with a number, right? No, it can't be a negative number. Definitely not. This would be a positive number. But here is where it's important to think about significant figures. Because there's uncertainty in this number, 5.50. The 0 is an estimation. And then we did this calculation, and we ended up with this having uncertainty over here. But when we look at significant figures and we subtract these, we end up with 0 within the uncertainty of the measurements. And so based on that, we're going to say there's no oxygen in this compound. And that's actually true. Benzene doesn't have any oxygen. It's just carbon and hydrogen. And if you did the calculation, what you'd end up with is really crazy numbers. So we just have carbon and hydrogen. I'm going to get rid of this stuff down here because I need some space. We have masses now. How do we calculate the empirical formula? Convert to moles and then find the ratio, right? So we've got our no, that's not going to be enough room. 5.07307 grams of carbon times 1 mole of carbon divided by 12.01 grams of carbon. .07307 divided by 12.01. 0.422404 moles of carbon. And then a similar calculation with the hydrogen. 0.42634 grams of hydrogen times 1 mole of hydrogen divided by 1.008 grams of hydrogen. 0.42634 divided by 1.008. 0.422956 moles. Those are really close, aren't they? Better safe than sorry. Let's go ahead and do the dividing. So this one divided by itself, because that one's the smallest, that's going to be 1. And then this one, .422404. 0.422956 divided by 0.422404. That comes out to be 1.0013. Also very close to 1. That tells me that the empirical formula is CH. I'm going to erase this stuff up here because I need some space. So we found the empirical formula, but what's it asking for? What's the molecular formula? And the empirical formula. So that is one of the answers. There's our empirical formula. The molecular formula is going to be some multiple of that. C2H2, C3H3, something like that. What we're going to do is we're going to take that empirical formula, 12.01 plus 1.008, which gives us 13.018. And we're going to see how many of these fit into the 78. 78 grams per mole divided by 13.018 grams per mole. The units cancel out. 78 divided by 13.018 equals 5.9917. This always has to end up being a whole number. And so you're going to round that to the closest whole number. So that's going to be 6. So that tells me that I take this one and I multiply all the subscripts by 6. And so I get C6H6. And that's the molecular formula. That's the molecular one, and this is the empirical one. Any questions?